techniques to break industrial control systems in new and interesting ways. So I currently work for Digital Bond Labs. I just am starting with Digital Bond Labs in July, although right now I'm presenting under the guise of cyber pacifist, so anything I say doesn't necessarily reflect my employer. So my background is I'm a former government guy, so I did stuff for the government for a while. Black bars. For 5 years, I worked for an electric grid protection manufacturer, so helping them make more secure devices to control and protect the electric grid. And then I've spent 3 years now as a security consultant. I started consulting for Digital Bond, doing all industrial control systems, security engagements. Then I worked for IOActive for 2 years, both as a consultant and part of their chief security officer team. Now I've taken a new position at Digital Bond where I'm going to go back to breaking strictly control systems again. So today I'm going to be talking about some kind of neat little hacking tricks, and this is kind of what I'll be talking about. You know, where we are on the network and what a control systems network looks like, what's happening at that level of network, what kind of problems exist there that have both been looked at before and haven't. Why the current way of securing these control systems devices are not so great, and kind of answering a challenge that a friend of mine in the space threw back in January. So this is kind of a typical control systems network. You know, you'll have your corporate network, what a lot of people call the L4 network in the Purdue model, right? That's where all your corporate computers sit, where you get your company email, that kind of stuff. And you'll have a firewall that will be protecting all of the control systems components. They're like usually really gooey. So all the control system stuff lives at what they call L3, L2, and L1. So this is kind of the layout of the network, and where I'm really looking specifically at securing the network is down here at these lowest layers, what they call the level 2 and level 1 of the control systems network. So some of the components that live down there are a PLC. People heard of a PLC before? Yeah, so that's way down at the bottom of the screen here. They're these little industrial controllers that do automation. So they're usually like an industrially hardened device where they have inputs and outputs that connect to this little tiny, usually kind of crummy microcontroller, but nowadays they have Ethernet in them too. If you've done any programming on an Arduino, it's pretty similar to that, although there's a standardized language that all PLCs use for doing programming. So really a PLC, it's good to think of it as the place where your network interfaces with the physical world. So you have inputs coming in, getting digitized and getting put onto your computer network, and then the PLC will do some automatic control to operate things in the physical world, and also can take commands from people on your network using operator stations. So the other kind of components that live down at this layer, one of them would be a human-machine interface. So it'll either be like a touchscreen or a mouse and keyboard with a graphical representation of your process, so you can kind of click on things and operate things and see how your process is going as far as producing widgets or pumping water or oil or gas or whatever it happens you happen to be doing. An interesting note about these systems, because I go and do assessments on these control systems all the time, usually people don't apply patches to any of the systems that live down at these lowest levels of a control systems network. You'll even find stuff that's vulnerable to like MS-08, 067 all the time, just because it's just not part of the culture of control systems operators. Their kind of focus is, let's protect these systems and prevent them from being talked to by anybody if we can, not so much on hardening the system itself. Another one of the systems that you'll have living down at this low level is what they call an engineering workstation. So this is the guy that's used for programming those automation commands into a PLC. Usually it'll be a separate computer. Sometimes they don't always leave these things plugged into the network all the time. A lot of times it's like a laptop or something that's turned off most of the day, stored in a shelf, and only brought out when they actually need to update a PLC's program. Again, this system isn't usually patched. A lot of that's cultural. Again, it's like if you patched this thing and it stopped working and then something went wrong on the plant floor, you would be kind of screwed as an operator because you're now not making widgets and you're not making money for the company. So patching equals bad because it's like risky. So other systems that might live down on the level 2 network, you might have multiple HMIs and engineering workstations depending on like how big a control system you're looking at. You also have these other things called OPC servers or real-time servers. Sometimes HMI systems directly communicate with PLCs. Sometimes they go through one of these intermediary servers. And then you also have some like data historians and stuff that will store like the state of your process, you know, back at least a day, sometimes weeks, months, years. So you can kind of look at the past of your process control system and kind of use that to help you predict, you know, what the future will be. It's especially important for stuff like the electric grid. So the stuff that lives higher, like closer to the corporate network from L2, usually you'll have, you know, domain controller, some file servers, some other file servers, and yes, you see this stuff in the field all the time. You know, there will also be data historians for, you know, kind of getting historical data up closer to the corporate network because, hey, your chief financial officer wants to know how many widgets you're producing, and he wants to know that every day so that he can help make projections for sales and stuff. Again, a lot of these systems aren't typically patched just because they're, you know, once again, required for the process to work. Like if you patched your domain controller and for some reason it didn't reboot, now, you know, if an operator accidentally rebooted their human-machine interface, maybe they won't be able to log in if they didn't cache credentials or something. So you don't patch these systems because everything works and we don't want to touch them. So the firewalls that live between these levels, again, there's firewalls between all levels of this network. So you'll have a firewall between your corporate, typically a firewall between L3 and L2, sometimes a firewall between L2 and L1. The firewalls are usually really, really permissive. And a big part of that's just culture, right? A lot of these guys are good at operations and they don't really know IT. They don't really understand protocols. They don't really want to. So they just say, well, our domain controller needs to talk to our L2 workstation. So just plug in the IP address of the domain controller and plug in the IP address of our HMI station and say they can talk to each other on any protocol, any port, because I don't feel like figuring out what they actually need to communicate with each other. And then there's other reasons that you have these any rules, and there's like some control systems protocol that uses ephemeral ports. So you know, a lot of times you just have these any rules living everywhere. So again, that's kind of how our network works. So the PLCs, because we're looking down at like the level 2 HMI systems and the level 1 PLCs, PLCs are insecure by design, right? These things were originally designed and deployed in the 1970s, and they really haven't changed since. In fact, I was just reading a little history on PLC devices, and the first PLC was installed about this time in 1970 by General Motors in one of their plants. So, you know, Dave Kennedy was talking earlier today, if you caught his talk, that like IT security is about 10 years behind, like on the defensive side where it needs to be. I think ICS security is 44 years behind where it needs to be on the defensive side of security. And there's been a ton of talks about PLC and security over the years. Ralph Langner talks about this a lot when he analyzes this virus that shall not be named because I don't want everybody to drink. There's another guy named Dylan Beresford who gave a talk a few years ago. I think he was supposed to give it at Takedown Con. It got pulled by the Department of Homeland Security. They claimed that it would be too harmful to critical infrastructure. He ended up giving the talk at Black Hat about Siemens PLCs. There's this thing called Project Basecamp that I took part in when I was with Digital Bond the first time, where we like owned a whole bunch of different field devices. And then there's like this other group that goes out and talks about Siemens prison controllers and how bad they are and how you could actually open lots of prison doors because there's no authentication on the protocols. So this is part of Project Basecamp. The D20ME, it's pretty unsexy device. It's what's called a remote terminal unit. This thing actually controls, I would guess, a little over 50% of the US electric grid. So chances are 50-50. If you drive by a substation, it's got one of these bad boys in it, and it's what keeps your lights on, you hope. So this device had like tons of vulnerabilities in it. It was really easy to cause it to crash. It was really easy to retrieve a list of usernames and passwords out of the device. And then you could upload your own logic to it, and then you could tell it to, you know, open the circuit breaker and shut off lights to people. This was another one that's pretty commonly used in critical infrastructure. This one's more common, I guess, in water than in electric, but this is called the Modicon Quantum. A lot of the same problems. You know, it had some backdoor accounts that let you log into the PLC, upload new logic, upload a Trojan firmware, all that fun stuff. This was another one. This is made by Alan Bradley, their control logics line. Yeah, nice fail light on their Ethernet controller. So this was kind of the output of Project Basecamp. So Project Basecamp was this thing that, you know, we had a whole bunch of researchers that worked on it. We looked at the top kind of 5 manufacturers, and the output of this was kind of a pass, questionable, and fail. So the red X's here are categories for where devices failed miserably at tests. So, you know, if a device was able to easily have malicious firmware uploaded to it without authentication or using a backdoor, it got a red X here. If it could have ladder logic easily uploaded to it, so like a new recipe for your plant floor without your authentication, it got a red X. There were lots of devices that had backdoor accounts. So if they had like an FTP server or a web server for configuring the device, you could log in and with a hard-coded backdoor that even if you know about it, you can't change. You know, these devices crashed when people fuzz tested them. There were just all kinds of stupid problems. So the reason I wanted to look at systems down here at the level 2, level 1 network is I've been looking at the hardware and firmware of a lot of the industrial controllers themselves for a long time. But about a year and a half ago, a company called Tofino let me borrow one of their field device firewalls. So this is a little application layer firewall that sits in front of a PLC and actually looks at the protocol that you're using for doing command, control, and status checking to the PLC. And they wanted me to give it a hard shake and give a talk on it, so I did. I actually liked their firewall quite a bit. They did do good protection, so they allowed you to set up, you know, a certain class of controller from which you could only read the status of the world. And their device did a good job of, you know, protecting you from issuing write commands or using any of these backdoor features that a lot of the PLCs have. I really kind of was impressed with a lot of their, you know, management software and some of the anti-reversing techniques they did. But one thing that they didn't do is they didn't add data integrity to any of the protocols. So, you know, when I gave the talk talking about the Tofino firewall, I said, well, there's really 2 problems with it. One, I can tunnel. So I wrote a IP over Modbus, which is a commonly used control systems protocol tunnel tool, and said, well, you could like throw a Raspberry Pi on your control, your level 1 network, and then you could use this software on the level 2 network and actually tunnel IP packets inside of Modbus. It would look like legitimate traffic, and the firewall would let it through, and sure enough, that works. Another tool that I wrote was this Modbus VCR that I finished off, and that's kind of where this talk really gets started. So this is just a quick shot of the Tofino hardware. They actually didn't have JTAG exposed. They had a BGA CPU. They did have some external SRAM here, but they told me I wasn't allowed to tap into it because they wanted to keep the hardware for themselves when they were done. I have some suspicions that if I was able to hook up to the address and data lines of the SRAM, I might be able to capture a firmware image or something like that when the device boots up. So if anybody wants to loan me a Tofino that I could actually hack for real, that would be cool. So what's going on at that level of network? You have a couple types of operation. There's the typical HMI stuff. So the HMI is going to be querying these PLCs and reading the status of the world. So it's going to say hey, what's the pressure in the pipe? What's the temperature of the beer mash or whatever is going on? It's going to be issuing write commands, which are causing outputs to get written. You know, if you want to manually override the application in the PLC, you might say, well, this batch of beer is bad for some reason. We all cry. But you click the button to open the valve so that the mash tun or whatever empties out. And there's the engineering workstation stuff. If you find you need to change your application, it's running in your PLC, you have to fire up the engineering workstation and you know, issue commands to the PLC from there. The trouble is that a lot of these protocols were designed in the 1970s and early 1980s, and most of the protocols used today were designed for use originally on serial networks. So back in the day, plants, there was no Ethernet back in the 1980s. Plants would roll out an RS-485 network, and they would hook up these PLCs to the RS-485 network. And, there was no internet back then, so they just kind of made this assumption, well, it's in the plant. We have physical security guards outside the plant to make sure nobody bad comes in. So we don't really need to do this stuff like authentication, because what's the point, right? If you're in the plant, you'll just throw a cup of water on the machinery and cause it to blow up. Why would you want to break into a controller? And the data integrity in all these protocols is really about noise. So it's just checksums. CRC16, CRC32, some of them do just, additive checksums, like 1 byte additive checksums for a lot of the protocols. So fast forward to the 1990s, and everybody wants Ethernet now. So they're like, oh, we have our PLC, we'll just slap an Ethernet card on there. And what do? We're engineers. What do? Do we want to write a whole new protocol, or do we just want to take that protocol that we had and wrap it in TCP and call it good? Well, everybody decided to just go that route because it's easy and they're lazy and they want to ship this product out in like a year, not in 5 years. So they didn't, they just wrapped these protocols in TCP. They didn't add any security features, and they just kind of told their customers, like, don't connect these things to the internet. And sometimes they would add backdoor services too, because their new Ethernet card maybe crashes, or like the control system's packet parser crashes. So they're like, well, we need a way to remotely reboot this, so we'll add this extra service that you can just like connect to, and it'll reboot the card or whatever. So they did a lot of that kind of stuff too. And again, this is kind of the result of what happens when you don't think about security. So Modbus is this protocol that is really typically talked about. If you go and look at any of the black hat talks that have talked ICS or SCADA, this is kind of the protocol that they use for analyzing control systems. And there's a lot of reasons for it. One of them is the packet structure is really simple. The specification is available from the modbus.org website. So you can download the complete protocol spec for free. It's a small command set. Wireshark can parse it. They don't do any of this crazy stuff. There's another protocol called DNP3 that does it basically implements the whole ISO stack inside of a TCP packet, and then it's you can do all this transport and application layer fragmentation on top of TCP IP. So that gets really complicated. Modbus doesn't have any of that stuff, so it's much easier to write tools for. And the neat thing is, all of the control systems protocols have the same security posture as Modbus, which is they don't do authentication, they don't do data integrity checking. So pretty much if something works against Modbus, it's going to work against other stuff. So the way Modbus and the other protocols work, that's why the asterisk is there. It's really this is pretty much how all the protocols work. The way it works is you have a server, whether it's an OPC server or an HMI server, and it's querying a PLC through time. Right, so it's going to issue a request to the PLC and say, hey, what's the status of input 1? And maybe that's a temperature sensor for your beer mash. Then the PLC is going to send back a packet and say, hey, this is the analog reading from that temperature sensor. Then the HMI is going to send the next request and say, hey, what's the status of the heater? Is the heater on or off? And then the PLC is going to send back a little status that says, the heater is on right now. So then the HMI screen updates. Maybe it'll show the temperature in one corner, and it'll show a little red light, meaning that the heater is on right now. So this polling process takes a little bit of time, not very long, but obviously this is multiple packets going across the wire at once. So Modbus isn't really what you would call a real-time control protocol. You're getting these two discrete pieces of information they're slightly time separated. So if the heater element flicked on and off really quick, you wouldn't actually see it on your HMI screen. It's not super important, but it's something to think about when playing with control systems protocols. So how Modbus works is, these polling sequences are almost always the same, right? It's always going to be asking for the same pieces of information from the PLC in exactly the same order. So it's going to be hey, what's the status of a heater now? What's the temperature now? What's the status of a heater now? What's the temperature now? And it's just going to keep doing that. The values will jiggle around a little bit. and that's just natural variation in either like sensor jitter or real world jitter. You know, if you're looking at an electric grid, people might turn on stuff that uses electricity, so your current draw will go up, and you know, whatever. The real world is analog and jittery. So what's the problem? So, like I said, ICS protocols lack data integrity, right? So this is the Modbus packet format. Modbus has a couple of silly fields. I call them silly. The first couple of fields, there's a transaction ID. That's just a 2-byte identifier that's made up by the HMI system. Usually HMIs will increment this value. So the first request will have 0 for these 2 bytes. Second request will say 1. Third request will say 2. Then the next thing is a protocol ID. Usually they just leave that at 0. I don't really know what that's supposed to mean. Then there's a length field that says length of packet. So the length field is 2 bytes long. For historical reasons, Modbus packets, I think, are only allowed to have 255 bytes total in their data payload. So I don't think the most significant byte of the length field can even be used. There's a unit identifier that most vendors don't even use. They just don't even care what it is. Where the interesting stuff happens is this function code and then the data payload. So the function code being 1 byte, data payload being the rest of the data. But of note, there's no digital signature here. There's no crypto. So if you did a man-in-the-middle attack against this, you can spoof data really easily. And remember, kind of like the assumption I've been making here is that, okay, this field device is protected by a read-only firewall, so it's going to prevent me from issuing any other kinds of bad commands to the controller. So these are what the Modbus function codes mean. There's, you know, like I said, this 1 byte function code field. 1 through 4 are defined as different read commands. So it's whether you're like reading an analog value, reading a discrete value, you know, all the actual address that you're reading is all defined by the vendor of the controller. So function codes 5, 6, 15, and 16 are write commands. So that's how you issue an operator command to the real world: open a circuit breaker, open a valve, close something, whatever. There are two function codes defined by the Modbus standard for programming the PLC, for actually uploading new ladder logic to the PLC. I don't see that typically implemented by vendors. So the one vendor I've looked at that implements ladder logic upload over Modbus is actually Schneider. And for a little background, Schneider bought Modicon years ago, and Modicon are the people that invented the Modbus protocol. So I think if Schneider doesn't use function code 125, 126 for doing ladder logic upload, probably nobody is going to. So like Schneider uses function code 90 for doing ladder logic upload download, but you can also do like arbitrary file transfer with it, and their function code 90 has all kinds of neat features. You can like tell the PLC just to stop doing processing using that function code 90. So function code 90 is one of those like other functions. So the Modbus spec says, you know, 1 through 4, 5, 6, 15, 16, 125, 126 are defined. Anything else is up to you. Like if you want to make a vendor-specific function code, you use one of those other ones. And so that's what Schneider did with function code 90. I'm sure other vendors do similar stuff. You know, a few years ago, I heard a rumor of a GE digital relay. So that's a piece of equipment that protects the electric grid, having like a firmware update over the Modbus protocol. So you can do all kinds of crazy stuff over it. So the application firewall, like I said, it inspects the Modbus packet itself. It actually like checks out all those fields and makes sure things look legit. So like, remember how I said the length field is 2 bytes long, but the packet length restriction is really 255. It'll check to make sure that you're using a valid length field. It will make sure that like the total data that you're sending and the length field match up. And it can also make sure that the function code that you're trying to use is allowed. So when you try to send packets through the firewall that are not allowed, it blocks the request. It's actually like a transparent firewall. I don't know what you call that, like a level 1 or layer 1 firewall. But it'll actually, it pretends to be the PLC itself, and it just issues a TCP reset to both the HMI system and to the PLC. If the packet's malformed in any way, if any of the fields look awry, it'll do the same thing, block the request, issue resets to both sides of the communication. And it does a good job of that. So the most restrictive mode, read only, it's really pointless to make the firewall more restrictive than that, just because if you're not able to read information out of your PLC, why even have it connected to a network at all? So the Modbus VCR is pretty simple. So the way it works is we do ARP poisoning against the HMI and the PLC, and ARP poisoning did work fine through the firewall. The firewall doesn't care about seeing ARP flip-flops. That's kind of funny. Sniff and record traffic for a while. So, we record traffic and watch this kind of cyclic behavior that I talked about. The HMI is always requesting the same data points. The values are jittering, but you're getting the same data points at least. So after you're done recording, you overwrite future status updates with your previously recorded status updates. So you let both sides think that they're still communicating with each other just fine, but you're using ARP poisoning and a little packet overwrite foo to overwrite the status of the world. And I was kicking it old school. I was writing this little tool in Ettercap, and Ettercap's all kinds of fun. Oh, and there's another tool that I kind of released with this stuff, and it's tunneling IP over the Modbus protocol, which is also available on my GitHub thing. So Ettercap, if you don't know, was it's an old project. It was designed originally for stealing credentials. It's used a lot of times against Windows networks, so you can do like encryption downgrade attacks when a workstation user is trying to authenticate to a domain controller, so that you can get like an LM hash that you can then either use past the hash, or you can crack the LM hash or whatever. But it has a really nice plugin architecture, so you can write your own plugins, and you can hook the whole packet capture and forwarding engine in Ettercap. The kind of awful thing about it is that you write your plugins in C. I've heard that you can write plugins now in Python, and I know that the head of the Ettercap project has been kind of talking about that a bit, but I haven't seen a good tutorial on doing it. So I wrote my little Modbus VCR in C. Please don't hack me. So memory management for the win. So this is just the sniff and record parts of the code. I ask if the packet is a request. If it's a request, I allocate a request response pair. Then I stuff the request into the request part of the request response pair, and basically wait for the response to come back. And then the response I'm going to put into the response part of the request response pair. And this is all being stored on a global buffer. Anyway, the Modbus VCR does this. It does this attack for 10 seconds. Then once the 10 seconds is up, and for most small industrial control systems, 10 seconds is more than enough time to record lots of states of the network as they fly by. Once the 10 seconds is done, it just sets this global flag saying recording is done. And then once the recording is done, when it sees a new request come in, it looks up what the response should be. And then once it sees the response, overwrites the response data with the previously recorded response data, and then ships it out back on the wire to the HMI. So HMI is effectively blinded. One of the fun things with this whole process was there was a, you see way down at the bottom, maybe you can read it, maybe you can't, it says PO arrow flags or equals PO modified. So that tells Ettercap that the packet's been modified and that it needs to transmit a new mangled packet. Well, the Ettercap function, when I started writing this, was there was a send TCP function inside of the core Ettercap library. Turns out it was broken, and it didn't actually send the modified packet, so I had to fix that little bug. So there's actually not that much code to it, though, for all that I just showed, because if you saw, most of that was comments, because I'm kind of dumb. So aside from the Ettercap glue for actually doing the code hooking and importing all the Ettercap libraries and stuff, there's really only 150 lines of C, which isn't too bad. So like I said, I just store the stuff in a linked list. If I see the request, I look up the response. If I see the response, I overwrite the data portion. It's not really anything new, right? This is a plain text protocol. It's not super challenging, but I had never seen a tool like this for cyclic, what I'd call cyclic protocols. I mean, this is really targeted at an industrial control protocol, but the concept can be used for any cyclic protocol that's meant to give status updates. So, with the Modbus VCR, you can basically, this is what your operator will see, like the network is running fine, the control system is going great, even though maybe your transformer caught on fire because a guy shot it with a rifle and the transformer oil leaked out and it overheated. So this is the kind of stuff that you can hide with the Modbus VCR. Although I hate using the fire example, I'm a professional. And also people are always talking about making SCADA stuff explode, and I don't really like talking about making SCADA stuff explode. But that's kind of what tape loops is about. So, I mean, if the concept, if this concept of hiding what's really going on with the process sounds familiar, it should. Everybody can take a drink. There's Stuxnet on a slide. So there's an in the wild piece of malware, obviously Stuxnet, that does a similar thing against the control system protocol, and it's the Siemens S7 controllers that it does it to. The big difference here is that Stuxnet actually modified ladder logic in the S7 controller to do its attack, and you can block that ability to upload new ladder logic to the controller with one of these firewall things. And also, like, actually doing that ladder logic attack requires that you pretty much know everything about the process beforehand, right? You have to know what the ladder logic in the controller is going to look like so that you can know which of the input stats are important to spoof and what's not. The nice thing about the Modbus VCR method is that you don't need to know anything about the process. It'll just record all the traffic that it sees, all the status updates that it sees, and replay it. So if you have like 100 PLCs in your network all being pulled, Modbus VCR will record traffic from all 100 PLCs and replay exactly the same state to the HMI. That's kind of nice because it makes everything look consistent to an operator, right? If there was one PLC controlling, let's say, a dam valve, and another PLC was just monitoring, let's say, a water flow sensor, right? And you only attacked the PLC that controlled the dam valve, and you told that PLC to close the valve. Well, the operator will see that the valve is open, but they'll also see that there's no water flowing past the water sensor. So they're going to know something's up and something's screwy. But with this method, you're recording everything and replaying everything. So the status that you recorded is what they'll see. It's kind of nice. So other protocols that are vulnerable to this, pretty much everything. So there's a protocol called IEC 61850. It's used in substations all over the United States and Europe. There's one called 6870 that's mostly used in Europe, although I heard a rumor that some places in the southeastern United States also use it. It's also, so 6870 is also this protocol that's used in what's called the Inter-Control Center Protocol, or ICCP. It's what all the energy management systems in the world pretty much use for talking to each other, so that they know, like, okay, you're a generating station and you're generating this many megawatts, and I'm the grid authority, and I see the transmission lines are doing good, and that transmission line's out of service. So that's the protocol that's actually used for all this stuff, and it actually does float over the internet, although obviously there's a lot of firewalling going on those systems. And kind of the reality is there's this encryption standard called IEC 62351 that you can tack on to 6870 to basically add SSL to it. There's only one vendor that does it. They are an ICCP vendor. If you really Google, 6870, 62351, you'll probably find out who they are. But there's no field device support. So there are field devices that speak this protocol, and they're kind of screwed. So there's another protocol called Ethernet IP. That a lot of PLCs use. That's also vulnerable. Lots of manufacturers make up their own protocols, and they're all pretty much all vulnerable to the same style of attack. Then there's DNP3. So DNP3 is the one that I kind of have the highest hopes for. DNP3, as it's implemented in most devices, is vulnerable to this. There is this thing called DNP3 SA. So it's SA means secure authentication. It's another one of these kind of like TLS add-ons to a classic industrial protocol. It adds authentication, and it actually does mutual authentication of the field device and the HMI or OPC system. Right now, not a lot of vendors implement it, but there's this guy who's been doing a lot of DNP3 fuzzing the last couple of years. If you're like a reader of the ICS CERT advisories, his name's Adam Crane. Like, almost every advisory related to DNP3 has been him and his buddy Chris Sistrunk. But he's just won a contract to implement DNP3 SA into the OpenDNP project. So I'm actually really, really hopeful that this will get adopted by lots of vendors and maybe save those devices from this kind of attack. So there's a proof of concept plugin available on GitHub. That's the GitHub link. Right now, the plugin just records for 10 seconds, then it starts replaying. You can adjust that time. It should be pretty obvious, I hope. The source is self-documenting, I swear. It should be pretty obvious, like, where to edit the code to make that change. Right now, it searches and searches and matches the entire Modbus packet. And if you remember, like the slide a while ago, said that there's a transaction identifier and like a unit identifier. You might want to modify the code if you were actually going to use this in like a real-world demo or something. Probably want to modify the code to ignore those couple of bytes when doing the packet matching, because otherwise it won't work. And I kind of like decided, well, I'm going to leave that version up on GitHub because I'd rather people have to download it and at least know how to program a little bit of C to make it work than just be able to download it and run it against anything they find. And definitely special thanks to Emilio Escobar. He's the guy that now runs the EtterCap project. Like EtterCap kind of sat dormant for a few years and didn't seem like there was a lot going on with it. But the last year or two, I'd say, has really seen a renaissance, and it's thanks to Emilio and some of the new guys that he's brought in. They're all really friendly. They're like, oh wow, yeah, we need a patch for that, and you know, you write them a patch and things work, and they're happy and you're happy and everybody's friends. So what are we doing about security now, and why does it suck? So right now, what we're doing about PLC security specifically, and these kind of level 2 systems specifically, is really just application firewalls and other firewalls. And you know, I kind of designed this attack because of the application firewall being pretty good, and I wanted to show that there were still problems. So an application firewall alone isn't going to help you here. Really, if you want to protect your network from this kind of attack, you need to do ARP poison detection. And so when I first talked about this idea before I released the tool, I was at a security conference called S4, and it's the SCADA Security Scientific Symposium. And like its name sounds, it's very like SCADA and industrial control systems specific. So there were like 120 people in the audience and like a lot of people that actually run control systems networks. And I was like, hey, so how many of you guys actually do like ARP poison detection on your networks? And one guy raised his hand, and I was like, so what caused you to start doing that? And because I kind of figured his answer would be, oh, we got hacked one time or something. But then he kind of put down his hand. He's like, well, we're thinking about it. I'm like, okay. So I mean, these are like the smartest guys in the ICS space, right? These are definitely the most proactive guys. They're like paying big money to go to Florida and talk to ICS security researchers and like, you know, do all this networking, and they're not doing this thing that a lot of people have talked about in the IT security world for a long time. So, and kind of another thing that makes this a little bit more relevant maybe is you know, a lot of these control systems are like really geographically spread out, right? I've been on field sites like in the middle of nowhere America, you know, with some little PLC in a shack that's helping run like either an oil pipeline or whatever. And you know, this little shack doesn't have a gate around it. It doesn't even have a lock on the door. And that kind of surprised me when I saw that one, because I was like, hey, why isn't there a lock on the door? And the guys that ran the place were like, well, you know, we have an alarm on the door. And one time the alarm went off, and you know, some like meth heads or something broke into the place. They had kicked the door down and then, you know, smashed everything in the control house. And he was like, well, they did all that, and by the time a cop could get out to even check on it, it was like 4 hours later. So, of course, the guy was long gone, whoever did it. So he was like, we decided at that point that we weren't going to lock any of our little outbuildings anymore because, you know, not only now were we down $10,000 worth of PLC gear in this control house, but now we were also down a door. So it's like better just to leave it unlocked, because if somebody wants to do something bad out in the field, they're going to do it, right? So, yeah, and that's kind of one of the fun, hard things about industrial control systems. So there's some other devices that do bump-in-the-wire encryption. So that actually will do like, you know, it'll be some little encrypting transceiver that sits in front of your HMI, and then another one sits in front of your PLC. And those are kind of nice. One downside to them is that they're all or nothing. So like, if you pwn the HMI system, now you can have the encrypting transceiver just encrypt the packets, and then they'll be decrypted correctly to the PLC, so you can do all the bad stuff still through there. And the other thing is they're really expensive, so it's like you have to buy hundreds of these little encrypting transceivers to sit in front of all your devices, and then it's like hundreds of more stuff that you have to like manage out in the field. And if you're an operator that doesn't necessarily have a lot of IT expertise, managing encrypting transceivers and managing keys and having all these field devices out there is probably not going to help you a lot. What we're mostly not doing about it is doing mutual authentication. So making sure that the HMI is verifying that the PLC is who it says it is, and the PLC is verifying that the HMI and engineering station are who they say they are. It'd be nice to see more protocols doing like digital signatures, at least on the protocol, to make sure that packets haven't been tampered with. So Siemens is like the only company that's making actual controllers that attempt to do this. They have a new line that came out after that virus that shall not be named was out in the wild. Their new controller line's the S7-1500, and it actually just uses off-the-shelf stuff, right? So the S7-1500 actually runs OpenSSL, and it just wraps both the HMI status update packets and the engineering packets in SSL. And of course, they actually just got hit with Heartbleed because they were running OpenSSL 101 on their PLCs. I haven't gotten to play with one of these Siemens controllers to see like how they're doing key management and all that stuff, to see if they're really as good as they claim to be on paper. It'd be nice to play with one someday. I doubt anybody from Siemens is here, but if you are, talk to me. So the kind of challenge, the gauntlet as we call it. So Jason Larson is this really smart guy in the ICS and SCADA security space, and he gave a talk at S4 this year in January. And he said, one of the things that we don't really talk about in the control system space is like, how would a bad guy profit from breaking your control system, right? He's like, most of these talks that go on at Black Hat are like, oh my God, SCADA, like I broke your control system and now I'm going to make $1 million. But what did you actually do? So it's kind of like, it's like I say, like everybody that claims hacking SCADA is all about cyber war and the world's going to end and I'm going to shut off all the power to the United States, they miss a lot. So I like to ask this question now. It's like, who knows when the last purely destructive piece of malware was found in the wild? Anybody have any guesses? I mean, besides Stuxnet. Close. Oh, I hadn't even heard of that one. Okay, so the answer that I had was from 2005. It was this one called Blackworm. I got that answer from Mikko Hyponen, and I just asked him the other day on Twitter, and he was like, oh, the last one that I know of in the F-Secure database is this one. So all that did was overwrite files on your hard drive. So it would look for like Word documents, Excel spreadsheets, PDFs and stuff, and just overwrite them with this fixed message. Didn't have any kind of blackmail aspect to it. It didn't like pop up a warning and say, send $500 to this account or I'm going to delete your files. It just did it. There really aren't that many pieces of malware that do it, right? So, Slammer 2005, 2003 or whatever it is in 2005, a South Korean one in 2009. Like people don't usually do this anymore now. Hacking is all motivated by profit. So I've been thinking about, how would you actually profit from spoofing the status updates from a control system? And I was like, well, I don't really know energy markets. I should say that first off. Like I'm not a power systems trading guy, but I was like, well, I kind of maybe sort of understand how energy markets work in a very rough sense. And I was like, to me, energy markets are what I like to call a predictably variably priced commodity, right? So generation stations generate power, and they have to deliver a certain amount of power throughout the day. And obviously, in the morning, they have to deliver a lot more power. And in the evening, they have to deliver a lot more power. But late at night, they don't have to deliver as much, right? So when these generation systems generate power, they actually have to kind of bid at what price they're going to produce power at, and then somebody has to go and buy the power from them. So obviously in the morning and the evening, a generation station can make a bid that's a higher price, right? Because there's going to be more demand for electricity in the morning and the evening than at the late night hours. So they can, they can charge more money at those times for generating electric power. I kind of got to thinking about some of this and, talking to some friends about it. And we were kind of like, well, what about wind? What about some of these renewables? So I was thinking, all right, let's say I'm an evil guy and I own this coal plant, like in Indianapolis, for example, and then there's a wind farm up north in Indiana, and I want to make as much money as I can running my coal plant, and I don't want those guys that make wind to make more money than me. They'll put me out of business, maybe. So if I was a bad guy and decided to break into the wind farm, I could maybe, this requires a lot of work and some kind of feeling out like how their network works and what kind of other security protections they have. But I kind of stuck in the back of my mind is like, could I actually spoof how much power they're feeding into the grid during those peak times to say that the wind generation guys aren't putting as much power into the grid during the hours like the early morning and early evening hours, and that they're putting more onto the grid late at night when power is not worth as much, right? So the accounting would, in the end, work out because me as the coal plant producer and them as the wind power producer, like the total electricity in megawatt hours that we're both producing lines up at the end of the month, but we're just kind of doing some offset. So I'm pretending to produce more power during the peak time and actually not producing much, and then I'm producing more at the off-peak time or whatever, So I'm making more money because I'm dealing with peak prices than my competitor. So I was going to put a little graph to show how that worked, but I didn't feel like making numbers. They're hard. So again, this is just, if you're a producer, you would use this kind of attack to spoof producing more during peak pricing. If you're a consumer, spoof using less during peak pricing. And the whole idea is just kind of try to do like a temporal offset of how much of this predictably variably priced commodity you're using. So for some more talks on like this, control systems hacking, especially at this low level, I definitely recommend checking out Project Basecamp. Dylan Beresford, Ruben Santamarta, Jacob Kitchell, myself, and then 2 anonymous guys worked on Project Basecamp and did a whole bunch of hacking. Jason Larson gave a great talk this year. We called it the Triangles talk. He basically took a wireless sensor, wrote about 200 extra bytes of code hooked the firmware in the sensor so that the sensor would produce reasonable looking spoofed data, including like adding noise to the data that was completely made up. It was, it kind of looked at what the sensor had seen in the past and then just spoofed new data that kind of looked like the old data, but added jitter and stuff to it. So it was pretty neat, and he did it in a tiny, tiny amount of space, so he wins. Kind of the conclusion is exploiting control systems in a way that makes money is hard. Fixing control systems is even harder. Anybody who says otherwise is probably selling something. And if you need control system consulting, call me. No. Okay, and that's all I have. So any questions? Yeah. To like, if you wanted to roll it out as a user? Yeah, so I think, I really don't know. I know that they produced an updated firmware. And I also know that the firmware that they produce is an update for the Ethernet board of that product. So kind of the nice thing about the modular design of a lot of PLCs is they'll have like one module that actually runs the ladder logic and another module that does all the Ethernet stuff. So, if you need to replace just the Ethernet part, you can do that without shutting down your process sometimes. And sometimes you can update the firmware in that thing without shutting down your process. But yeah, it's kind of a trouble is like if you have a bug like this in a PLC and then you need to update your PLC, a lot of times it will still require, like, to be safe, taking your whole process offline. So that's another part of the reason people don't patch. It's especially prevalent at the device level because it's like, well, we have a plant shutdown maybe once every 2 years. That's when we have a chance of applying patches, but an operator is only going to apply the patch if they also have enough money for like a test control system where they can like validate and make sure that the patch isn't going to screw everything up. So, good question. Any others? Okay, well, thanks. Appreciate it.